Hello, hello, hello,
Hello, hello.
okay. So, good evening. My name is Devarun Banerjee. Welcome to the live session of this NPTEL course, Physical and Electrochemical Characterizations in Chemical Engineering. This is live session number 6, and I am a PhD PMRF scholar of Indian Institute of Technology, Delhi. So, in this week, the fundamentals of rheology and some basic principles of rheology were covered as per the content of concepts of stress and strain, constitutive relation, rheometers and measurement techniques, uh, etc. So, rheology is the study of matter's flow and deformation. Professor E.C. Bingham of Lafayette College in Indiana invented the term rheology in the 1920s. Uh, Flow is a type of deformation. Stress deformation relationships are material attribute. So when you talk about the liquids, the defining parameter for this flow deformation is viscosity, which is the ratio of stress and shear rate. For solid, it is modulus, which is a ratio of stress and strain. And the materials which have the properties of both these types are usually called as viscoelastic. So if we take an example of simple shear flow where the bottom plate is stationary and the top plate is moving with a velocity v naught and giving it is moving by virtue of a force F, then you can call that the shear stress is in sigma, which is the ratio of force per unit area. The shear strain in percentage, uh, gamma is equals to the x, which is a function of time. So in x direction, how much it is moving divided by in y direction, how much is the y direction, basically the difference between the two plates, bottom and top. And shear rate in second inverse is basically the ratio of shear strain and time. And this particular ratio of shear stress and shear rate is called the viscosity. Eta equals to sigma by gamma dot is equals to shear stress by shear rate. So a rheometer is a device that may be used to determine the viscosity of fluids, semi-solids and solids. It may give information on the material's properties such as viscosity, which is defined as a material's resistance to deformation and is proportional to the shear rate or stress. Viscosity is dependent on both time and temperature, and viscoelasticity refers to a material's attribute of being both viscous and elastic. G dash G double dash, tan alpha. These are the values which are determined in terms of time, temperature, frequency, and stress or strain. So a rheometer, what does it measure? When we talk about the rheology, so it is basically the study of matter flow and deformation. Stress analysis, which is basically the force per unit area and its relationship with deformation. So what do we mean by deformation? It is basically denoted in the terms of strain or strain rate. Apart from that, what are basically the measurements are important in the rheology? So torque, which is basically the equivalent to the force, angular displacement, angular velocity. So these are the most important things. So if we take the flow in parallel plates, right? Then if the R is basically the plate radius, theta is the angular motor deflection in radians, omega is the motor angular velocity, h is the basically distance between plates. Then stress, which is sigma equals to the 2 by pi r cube into m. M is basically the moment of inertia in micronewton to meter. Strain equals to r by h into theta. And strain rate is r by h into omega. Omega is motor angular velocity. This is an example of this particular rheometer. So in a rheometer, the stress is calculated from the torque. So if you see the formula for stress is equals to m into c. M is basically the torque, and this c sigma is equals to the stress constant, and this particular sigma is equals to the stress. So stress equals to torque multiplied by stress constant. The stress constant is a quantity that is a geometry dependent. Shear strain. The angular displacement is applied through the rheometer in a generic rheometer. Strain is expressed as gamma equals to c lambda into theta, where gamma equals to strain, c lambda equals to strain constant, and theta equals to angular motor deflection in radians. The strain constant c lambda equal is a geometry factor. So the parallel plate configuration, C gamma equals to R by H. R is equals to this particular length of the flow of the material, and H is this particular in between layer thickness. So you use this equation to convert angular velocity in radians per second to shear rate at per second at the edge. This is used for angular displacement in radians per second to shear strain at the edge. C sigma equals to 2 by pi r cube for Newtonian fluids to convert torque Newton meter to shear stress at the edge Pascal. So the first question of today's is for a flow in parallel plate as shown below. The stress is given by 2 by pi r cube into m pi r to the power 3 by 2 into m r by h into omega h by r into omega. So basically if you see the formulas, stress is equals to 2 by pi r cube into m. That is the correct answer for stress. So strain is equals to r by h into theta. Strain rate equals to r by h into omega. With decreasing gap height in a parallel flow setup, the shear rate increases, decreases, remains constant, none of this. with increasing gap height, which is basically h, the shear rate will be increasing. So h decreases, it means the shear rate will be increasing. In a cone and plate type rheometer with increasing cone angle, shear rate will be increasing, decreasing, constant, none of these. So it decreases. If you see, shear rate is inversely proportional with beta, which is the cone angle. So with increasing the cone angle, shear rate decreases in the order of 0.5 to 2 degrees. Okay, is shown. The other lectures we discussed about basically some complex fluids, some case studies and their properties, such as the different complex fluids include Newtonian fluids, non-Newtonian or complex fluids, which include time independent, shear thinning and shear thickening fluids and viscoelastic fluids. Newtonian fluid basically it exhibits a linear correlation between applied shear stress and shear rate. And simply non-Newtonian fluid basically there is a departure from the Newtonian behavior. But when it occurs when the simple shear measurements do not traverse the origin and fail to establish a linear connection between the shear stress and strain. The apparent viscosity is not constant and is determined by both of these factors. These substances are variably referred to as simply viscous, inelastic, time independent, or generalized Newtonian fluids. So the time-dependent non-Newtonian fluids are those in which the connection between shear stress and strain rate is further dependent on the length of shearing and kinematic history. Systems show both viscous fluid-like and elastic solid-like behavior. So these are typically called as viscoelastic or elastico-viscous fluids. For example, this family of materials exhibit incomplete elastic recovery, recoil, and creep, among other properties. The non-Newtonian fluids include the generalized, like one example is generalized Newtonian fluids, which are either purely viscous, inelastic, and time dependent. Basically, these are the systems where strain rate is determined only through shear stress at that point. Uh, Shear thickening and shear thinning type of fluids are there. Time independent fluids, where the relationship between shear stress and strain rate is governed by the duration of shear and its previous kinematic history. Uh, it can be shear thickening or shear thinning, and then the viscoelastic behavior. They show a blend of elastic-like behavior and viscous-like behavior. Viscoplastic fluids, the existence of a yield stress or apparent yield stress that must be exceeded for the fluid to deform or flow. The material acts as elastic solid when applied external stress is less than yield stress, or flows like a mass, like a rigid body. External yield stress higher than internal yield stress causes Newtonian or shear thinning behavior. Newtonian means constant viscosity. At rest, the material is composed of three-dimensional structures with sufficient stiffness to resist any external stress less than the yield stress, forming a formidable barrier to flow despite its ability to bend elastically. However, at higher stress levels, the structure degrades and substances act like a viscous fluid. On the other hand, for time-dependent independent latent behavior, what happens? Uh, at rest, the suspension has a negligible void edge and the liquid content in the sample is sufficient to fully fill the voids. Then at low shear rate, the liquid lubricates particle movement, decreasing the solid-solid friction and resulting stresses. However, at large shear rate, the mixture expands, preventing a direct solid-solid contact and friction. This results in a formation of much greater shear strain and can provide both shear thickening and shear thinning behavior, such as thixotropic and rheopectic behavior are also there. In these curves, you can see that the curves of such a fluid is measured in a single experiment where the strain rate is progressively increased from 0 to a maximum value at a constant rate. If it's reduced at the same rate, then a hysteresis loop is formed. The height, form, and area encompassed by the loop are dependent on the experimental circumstances. The rate at which the shear rate increases or decreases, the shear rate's highest value, the sample's prior kinematic history are all included. For the example is thixotropic behavior. When sheared at a constant rate, the thixotropic behavior uh, of material is said to be thixotropic if its apparent viscosity decreases with the duration of shearing. As the strain rate is progressively increased, the time needed to reach the shear stress equilibrium value drops substantially. So if you see the viscoelastic behavior examples, there are certain examples like glass, concrete, ice, carrots, potatoes, bananas, and you can see the value of G, which is basically the constant value uh, to determine the particular strain stress, right? Like the stress and strain is proportional to that proportionality constant is G. So you can see the value of G is gradually decreasing with the softer material is used. Banana is much more softer than potato, then carrot, and gradually moving towards the harder material, ice, concrete, glass. The G value is also increasing from mega to giga. Okay. And for solid, there is this Hooke's law. The standard Young's modulus serve as the proportionality constant. Viscoelastic behavior. While most substances return to their former positions when stress is removed, many instances the full recovery does not occur and creep occurs, which means that the solid has flowed. Numerous materials used in engineering exhibit both elastic and viscous properties under the right conditions. A substance is considered to be viscoelastic if it lacks thixotropic and rheopectic effects. Clearly, the two limiting instances of viscoelastic behavior are completely viscous flow and totally elastic deformation. Another often utilized flow pattern to describe viscoelastic fluids is the oscillatory shearing motion. We can compare the response of a Newtonian fluid and a Hookean solid when a sinusoidal varying shear strain is applied. The mathematical form is given as gamma equals to gamma m sine omega t. And gamma is the amplitude, omega is the applied strain frequency. So the some further assignment for problems, sample problems we'll see. For the figure below, the A and B represent dash and dash respectively. Dilatant and pseudoplastic, pseudoplastic and dilatant, viscoplastic and pseudoplastic, Bingham and pseudoplastic fluid. So correct answer is viscoplastic and pseudoplastic. If you see this diagram, there is a yield stress for viscoplastic. So and there is no yield stress for pseudoplastic, but both of their pattern is same. So the B is the pseudoplastic and the A is the viscoplastic fluid. Which of the following statements are not true with respect to viscoplastic fluid? The existence of apparent yield stress but that must be exceeded for the fluid to deform or flow. The material acts as an elastic solid when applied external stress is less than yield stress. The external yield stress is lower than internal yield stress, causing shear thinning behavior, or all of these. The correct answer is C. The external yield stress is lower than the internal yield stress, causing shear thinning behavior. It is basically wrong for viscoplastic fluid. Correct. The external yield stress is actually higher than the internal yield stress, which causes the shear thinning behavior or Newtonian behavior. For the figure shown above, in a thixotropic behavior, as the strain rate is increased, the time required to reach the shear stress equilibrium value decreases, increases, remains constant, none of this. So the correct answer is decreases. The figure shown above, as the shear strain rate is increased, if you see, strain rate is increasing, okay, from bottom to top. So the time required to reach the equilibrium is actually decreasing. So gradually this particular time, if you see, this is much greater than this particular top line. So this is gradually decreasing to reach the equilibrium value. Today's last question. The oscillatory behavior of a fluid flow indicates a purely response. Option A viscous, option B elastic response, option C partially viscous, option D none of these. The correct answer is viscous. If you see this particular phase difference, the phase angle, if it is small, so small phase angles correlate to primarily elastic behavior, and if it's a large, it's a high phase angle belong to the viscous behavior. So it is given that it is a pure response. So the for a pure response, either it would be delta equals to 0 or delta will be 1. So here clearly it is delta is not equals to 0. There is a phase difference. So for this particular pure response, it is the viscous response. That is all from my side today. Thank you.